Hey students, Mr. Danahauer here. Today we're going to be talking about the periodic table and some of the trends that we notice on the periodic table. Now, this video lesson is going to take place of the lesson in your course pack that's titled Introduction to the Periodic Table. And we're going to focus on three main concepts in this lesson. The first one is going to be the simple trend for atomic number, which is also the number of protons in an element. The second thing will be the trend for atomic mass. And lastly, we'll spend a little bit of time looking at the trend for ions on the periodic table, which is going to be a really important concept as we move forward here. So let's start off with our trend of atomic number. Again, this is a fairly simple trend. If we look at the periodic table, and I've posted a simplified version here, what we're going to see is as we read or look at the periodic table and move through the elements as we were reading a book from left to right, top to bottom, we see that as we move from one element to the next, the atomic number simply increases by 1. So from hydrogen to helium, 1 to 2, lithium 3, 4, 5, 6, 7, 8, 9, 10. And as we cruise on and move through the periodic table, we can just see that it increases by 1 as we move from left to right, top to bottom on the periodic table. Again, the number of the atomic number is simply the number of protons in the nucleus for an element. And again, that's the identity of the particular element that we're talking about. So if we know that we have an element that has 26 protons, we can easily find it by counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to the box that represents the 26th box. And that would also be the element iron, Fe. And that element always has 26 protons. That's identity. So trend number 1, the trend for atomic number is simply that it increases by 1 as we move across the periodic table from left to right and we move down from top to bottom. The second trend we want to look at is the trend for atomic mass. So I have another periodic table here. And if we look at the atomic mass, I've simplified this periodic table as well. It only has atomic number and then the weighted average atomic mass, which we've learned about. So we see as we move across, the atomic mass is increasing. This makes sense, right? Because the atomic mass is composed of, it's basically a weighted average of the protons and neutrons of the different isotopes of an element. And we know that if we're increasing in the number of protons in the nucleus, the mass has to be increasing. Interestingly, the protons are positively charged in the nucleus, and there has to be something to sort of balance out those positive charges that want to repel each other in the nucleus, and that would be the neutrons. And so neutrons are in the nucleus, and there's a force involved in the nucleus there that actually, in a sense, glues the nucleus together, the different protons. And so the mass number, as we've talked about in the past, is the number of protons plus neutrons in the nucleus. So as we move across from 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10, as we add more protons, there also is a necessity for more neutrons to essentially glue all of those protons in the nucleus together. So the trend we see for the atomic mass, or weighted average atomic mass, is that as we read the periodic table from left to right and top to bottom, the mass is continually increasing. If we look for a specific trend there, or mathematical formula, if you want to think about it that way, for the first 3 to 4 rows on the periodic table, it's really, we increase the mass by 2 each time. So we're adding a proton every time we move from one element to the next, and we're typically adding 1 neutron at the same time. But as we get past about the 3rd to the 4th row, somewhere in here, we start to add a lot more neutrons. The ratio of protons and neutrons starts to increase. We have more neutrons than protons. The big picture here, though, is that as we go across from left to right, the mass is increasing, and from top to bottom in any group, the mass is going to be larger at the bottom, or the mass is going to increase as we go down a group. So again, the number of protons is increasing by 1 as we move across, and it is sequential. And the mass number, or the atomic mass, increases from left to right and top to bottom as we move across the periodic table. So those trends are fairly straightforward. The last trend we're going to look at that's going to take a little bit more discussion is the trend for ions in the periodic table. And there is a trend here. I've got a third periodic table we'll look at. So this actually shows us the most common charges for all of the elements on the periodic table. So let's talk briefly about why ions form in the first place. Remember that for an atom to be stable, it likes to have a full valence shell. And a full valence shell is typically 8 electrons in the valence shell. So we have a full outer S and P sublevel, and that is a stable electron configuration. Remember in this unit, the last unit on electron configurations, that most ions form a noble gas electron configuration. So elements that are nonmetals typically gain electrons to look like and have an electron configuration as a noble gas. And metals typically lose electrons to form an electron configuration of a noble gas. If an element has an electron configuration similar to a noble gas, it's going to have the full octet, a full 8 valence electrons. So metals typically lose electrons, become positively charged to look like a noble gas, and nonmetals over here typically gain electrons to achieve a noble gas electron configuration. Remember, we also call that the octet rule. So if an element has 8 valence electrons, it has a full octet. So let's just dig into this a little bit more and look for trends that we see. If we look at, let's just take the first group here, okay? The first group we know has 1 valence electron. So those elements typically are going to lose that 1 valence electron. And when they do, the next shell on the inside, the lower energy S&P sublevels, are full already. And so all of these elements typically gain a +1 charge. They've lost 1 negative electron, giving them a net charge of +1. So this group, remember that we call this group here the alkali metals. The alkali metals always form a +1 charge when they become ions. If we move on to the second group, which are the alkaline earth metals, they have 2 valence electrons. So again, metals are going to lose electrons in order to fulfill the octet. And all of these elements have 2 electrons in their valence shell, so they're going to lose both of those electrons. When they do, because they've lost 2 negative charges, they're going to have a +2 overall charge. So again, the alkaline earth metals always form a +2 charge whenever they become ions. So we see this trend. Group 1 always has a +1 charge. Group 2 elements always have a +2 charge. We can move over here as well to the group that aluminum is part of. And we notice that typically elements in this group have 3 valence electrons. Remember we said one valence electron, 2 valence electrons, 3 here. Okay. So again, because they're metals and they have 3 valence electrons, metals typically lose electrons when they become ions. And so aluminum, gallium, and indium are going to all lose 3 valence electrons and form a +3 charge. So we can see that trend. Metals in group 1, group 2, and this group here, they typically they have a set charge that forms. And that's predictable and it's consistent. Those elements always form those charges, and it's very unlikely that we're going to find them in nature with a different charge than what we've indicated here. Let's move on to the nonmetals. Remember, we have this dividing line here between the metals and nonmetals. So on this side are our nonmetals. Remember that nonmetals, you may remember that they have a higher electronegativity, or what we call electron affinity. And so they're typically going to take electrons to fill the octet. If we look at the halogen group here, those elements have 7 valence electrons. So in order to have 8, all they need to do is gain 1 valence electron to fill that p sublevel. So all of these elements, you'll notice when they gain 1 electron, they form a -1 charge because they have 1 extra negatively charged electron. That's consistent. all of our halogens form a -1 charge as an ion. If we move on to the oxygen family here, all of these have 6 valence electrons. So when these elements gain 2 electrons to look like a noble gas, they're going to have a net charge of -2. We can see that, again, it's very consistent. All of the nonmetals in the oxygen family are going to form a -2 charge. If we continue on, the elements in the nitrogen family have 5 valence electrons. Nonmetals are going to gain electrons. And so these elements that are nonmetals are going to gain 3 electrons to get to 8. So if they have 5, they need 3 to get to the octet with 8 valence electrons. And that's going to give them an overall net charge of 3-. Again, we can see this pattern, right? The halogens form a -1 charge. The oxygen family all forms a -2 charge. And the nitrogen family forms a -3 charge. That's consistent. And we're always going to find those elements as whenever they're ions, they're going to have those charges. There are, of course, exceptions to these rules, but in general, and for our purposes in this class, that's going to always be true. And you'll notice a few elements on here that don't have charges: carbon, boron, silicon, or noble gases. That's because there are some elements on the periodic table that are pretty unlikely to gain or lose electrons in order to fill the octet. Oftentimes, elements like boron and carbon and silicon, in order to fill their octet, they're going to share electrons in covalent bonds, which we'll get into later in our bonding unit. And of course, our noble gases don't gain or lose electrons because they already have a full S and P sublevel, except for helium just has the 1s sublevel full, but their valence shell is already full. And so to gain or lose electrons for those elements would not stabilize them. It would actually cause them to be less stable if they change their electron configuration. So they're already as stable as they can be. Now this brings us to our last groups of elements. If we look at this group here, okay, these are, let me change my pen setting here. If we look at this group here, okay, which we call our D block, or we also know these as our transition metals. Okay, the D block is the transition metals. What do we notice about the elements and the charges in the D block? Well, let's just take iron, for example. Iron actually can be found in 2 different ion stages. It can have a +2 ion or a +3 ion. So in nature, we find iron in both forms whenever it forms an ion. The same thing with nickel here. Nickel forms sometimes a +2 charge and sometimes a +3. Copper, we find in nature in a +1 charge and a +2 charge. The point is here that there are many elements in the D block that can have what we would say variable charges, or they can be found with multiple different charges, sometimes referred to as oxidation states. This presents a bit of an issue, especially when we get into naming and formula writing, but for now it's just important that you understand that our main group elements have predictable charges, but our transition metals, which I'll label TM here, our transition metals often can have multiple different charges. That's also true with our post-transition metals, which are going to be the metals that are past the D block and the P block, but they are metals. These elements here also can have multiple charges. So basically any element that's in the D block, any metal that's in the D block or the P block metals, with the exception of aluminum, those ones we're going to say that there are often multiple different charges that can exist for those metals. The same is true down here. You'll notice in our F block, all right, our inner transition metals, those metals can often have multiple charges as well. So we can see very clearly that there are some trends with ions in the periodic table. For our main group metals, which would be our S block of metals here, we know that group 1 forms a +1 charge and group 2 forms a +2 charge always. Also, aluminum forms a +3 charge. You need to know those and memorize those, and I would actually recommend that you put those charges, if you would take out your reference periodic table that we were working on the other day, and add those charges as a sort of a cheat sheet or a reminder of the common charges that those elements form in those different groups. And then do the same thing for our nonmetals here. Nonmetals, our halogens, always form a -1 charge, our oxygen family a -2, and our nitrogen family nonmetals form a -3 charge. That's going to be consistent, and I would recommend that you go ahead and write that on your reference periodic table so that you have that to remind you. You may also just want to make a note that all of these other metals in here can have a variable charge. The reason for that, we talked about the reason why the different main group elements, like these guys here, why they form a +1 or +2 charge because of gaining or losing electrons, and why the nonmetals over here form always their consistent negative charges. So why do the transition metals have the potential to form multiple charges? And this gets into electron configurations. You might have remembered we talked a little bit about elements in this group forming different electron configurations than we would expect. The point is that the D block elements can behave a little bit differently. Those metals, they can lose electrons sometimes from their D sublevel and move them into an S sublevel. They can lose electrons from a couple of electrons from their S sublevel. There's multiple ways that they can lose electrons to form positive charges. And the reasoning for that gets a little bit more complicated than we're going to get into in our general chemistry class. But for now, just understand that the D block elements and these post-transition metals here can form variable charges. Okay. So today's lesson, fairly short. We understand now the trend for atomic number, the trend for atomic mass, and a little bit more about the trends for ions, how they form, why they form, and that we know that there are some groups that form consistent charges for those elements. And then, of course, there are some elements, specifically the transition metals and post-transition metals, that form somewhat unpredictable charges, I would say. That's all for today. Hope you understand a little bit more about the trends on the periodic table, and Sko Ridge.